Good afternoon, everyone. Today I'm going to present a topic from computer networks called the domain name system, commonly known as the DNS. The DNS is one of the most important services on the internet and it plays a very crucial role in enabling users to access websites easily. In this presentation, I will explain what DNS is, why is it needed, how it works, and its real-world applications. So, what is a DNS? Now, the internet fundamentally works using IP addresses, which are basically numerical values that are assigned to each device connected to a network. However, remembering each numeric IP address is very difficult for humans. To solve this problem, domain names were introduced. Domain names are easy to understand and remember, they're very user friendly. A DNS acts as an intermediary system that converts these domain names into IP addresses so that communication can take place easily. So, what is the need for DNS? As the internet has expanded globally, the number of connected devices have increased rapidly. The IP addresses are not intuitive for human users. Managing these IP addresses manually became impossible. DNS provides a scalable and automated solution to this problem. It allows the users to access the websites without needing to know the actual IP address of the server. The DNS provides scalable and automated naming system, which is easier for the users. Without DNS, the users would have to remember numeric IP addresses for each website, which would make the internet unusable for most of the people. Now, let's take a look at the characteristics of a DNS. First, it's a distributed and hierarchical naming structure. This means that no single server handles everything here. The responsibilities are spread across multiple levels, from the root servers to the TLDs and to the authoritative servers. It operates on a client-server architecture where your computer, basically the client, requests information from DNS servers to resolve domain names. The DNS uses a database of resource records. These records store information like IP addresses, mail server details, and etc. It also provides name resolution and reverse lookup, which means it can not only turn domain names into IP, but can also find the domain name associated with the given IP. The DNS also supports fault tolerance and load distribution, which so even if some of the servers fail, the other servers can continue providing service, making the internet more resilient. Other notable characteristics include caching, like which speeds up related queries by storing the results temporarily, and scalability, which allows the DNS to handle the growth of billions of devices and websites without slowing down. Finally, extensibility is the key here. DNS can support new records and services as internet evolves, like IPv6, security extensions, and modern cloud applications. So let's talk about the DNS namespace and the hierarchy. The DNS namespace follows a hierarchical structure which helps to organize the domain names in a logical and scalable manner. This hierarchy ensures that the domain names remain unique even though the internet contains a billion of devices. At the top of the hierarchy is the root domain, which acts as a starting point for all the DNS queries. Below the root domain are the top-level domains such as .com or .org and country-specific domains like .in or .uk. Each top-level domain further contains a second-level domain, which can be used to represent organizations or websites. The subdomains can then be created to organize services within a domain. One important advantage of this hierarchy is the delegation of authority. Each level in the DNS hierarchy is responsible only for managing its portion of the namespace. For example, the root domain does not store the IP address, but simply directs the query to the appropriate top-level domain server so that it can store the IP address. This hierarchical approach makes the DNS highly scalable, and its new domains can be added without affecting the entire system. It improves fault tolerance since failure of one domain server does not interrupt the entire DNS infrastructure. Okay, so now we look at the root domain versus the top level domain. The root domain and the top level domain are the two important levels in the DNS hierarchy. The root domain is the highest level and is represented by a dot. It is not visible to the users, but it plays a very crucial role in directing the DNS queries to the correct top level domain servers. Below the root domain are the top-level domains, which are most commonly known as TLDs. These are visible to the users as extensions such as .com or .org, or like country codes such as .in or .uk. While the top domain, basically the root domain, acts as the starting point of the DNS resolution, the top-level domain acts as an intermediate guide, which basically directs the query towards the appropriate authoritative name server. Together, these two levels work together to ensure that the domain name resolution is efficient and well organized. So now the components of a DNS. The DNS system consists of several key components. The DNS resolver is responsible for initiating the queries on behalf of the client. The root name server directs the resolver to the appropriate TLD server. The TLD name server directs the query to the authoritative name server. And finally, the authoritative name server stores the actual DNS records and provides the IP address. Okay, now we come to the most important process of the DNS, which is known as the DNS resolution process. So when a user enters a domain name into a web browser, the DNS resolution process begins. The first step is not immediately contacting the root server. Instead, the browser sends the request to a local DNS resolver, which is usually provided by the operating system or the internet service provider. The resolver first checks its cache to see if the IP address for the requested domain is already available. If the record is found in the cache and is still valid, the resolver immediately returns the IP address to the client, reducing the delay and the network traffic. If the IP address is not found in the cache, then the resolver initiates the hierarchical resolution process. It first contacts one of the root name servers, which does not know the IP address but provides a referral to the appropriate TLD. Next, the resolver contacts the TLD name server, which further directs the query to an authoritative name server, which is responsible for the requested domain. The authoritative name server contains the actual DNS records and provides the final IP address. Once the resolver receives the IP address, it stores the information in its cache for future use and sends the IP address back to the client. The browser then uses this IP address to establish a connection with the web server and load the requested website. So now let's take a look at the recursive query and the iterative queries. The DNS queries can be classified into recursive queries and iterative queries based on how the resolution process is handled. In a recursive query, the client expects the final IP address as the response. The entire responsibility of resolving the domain name is handled by the DNS resolver itself. The resolver queries multiple DNS servers on behalf of the client, which keeps the client's workload very low. Because of this simplicity, recursive queries are commonly used by web users, web browsers, and end users. In contrast to the recursive query, the iterative query works quite differently. Here, the DNS server returns the best possible information it has, usually in form of a referral to another server. The client or resolver must then continue querying other DNS servers until the final answer is obtained. This approach, by using the iterative query, distributes the workload across the DNS hierarchy and is mainly used in communication between the DNS servers. Overall, the recursive queries focus on the ease of use for the clients, while the iterative queries focus on the efficient server operation. So the common DNS record types. The DNS information is stored in the form of resource records. Each record contains fields such as a domain name, a record type, a class, a time to live, and a value. These records enable the DNS to provide different services like web access, email routing, and aliasing. Resource records make DNS flexible and powerful. The common DNS record types are the A record, which maps the domain name to the IPv4 address, the AAAA record, which maps the domain name to the IPv6 address, the CNAME, which creates an alias for another domain, the MX record, which specifies mail server for the domain, and the NS record, which identifies the authoritative name servers. So now let's take a look at the advantages of DNS. First, it makes accessing internet resources user-friendly. Instead of remembering huge complex addresses like 172.217.3 etc., we just type in google.com and see that's like a very huge convenience for users like us. Next is the fact that its distributed structure ensures reliability. DNS servers are spread all over the world, so even if one server goes down, another server can take over and keeps the internet running very smoothly. Another very key point here is that the DNS is highly scalable, which is critical because the internet keeps growing every day. Whether it's billions of websites or like new devices coming online, DNS can handle the expansion without slowing down at all. DNS also reduces the dependency on IP memorization. Like imagine trying to remember hundreds of IP addresses. That would be impossible. So DNS lets us focus on meaningful names instead, such as the names of web browsers or whatever we're searching online. Finally, the DNS supports multiple services under one domain. For example, a company like Amazon.com can host its website, email servers, cloud services all under the same domain name, which makes management much easier. In addition to this, the DNS can also improve load distribution through techniques like round robin DNS, which helps prevent servers from getting overloaded and supports localization, directing users to nearby services to faster response times. So the DNS security issues. Now security issues are very important when it comes to computer networks. Although DNS plays a crucial role in internet communication, it was originally designed without strong security mechanisms. As a result, DNS is vulnerable to several security threats that can affect users and organizations. One common security issue is the DNS spoofing. Now, what is a DNS spoofing? A DNS spoofing is where an attacker provides false DNS responses, redirecting the users to malicious websites. This can cause viruses and other malicious software to get into the device. Another major threat is DNA cache poisoning, where the incorrect IP addresses are stored in the DNS cache. Once poisoned, the resolver continues to serve false information to multiple users, making the attack more harmful. The DNS attacks exploit the fact that the traditional DNS does not verify the authenticity of the responses. Because DNS operates on trust, attackers can impersonate legitimate servers and manipulate name resolution. These security issues can lead to serious consequences such as phishing attacks, data theft, secure service disruption, and loss of user trust. For organizations, the DNS attacks can result in downtime and proper financial loss. To address these problems, the DNS security extensions, known as the DNSSEC, were introduced. The DNSSEC adds authentication to DNS responses using digital signatures, ensuring that the data received is genuine and has not been altered. However, even that has its limitations. It increases computational overhead and complexity, and it does not encrypt DNS data, it only verifies the authenticity. Therefore, the DNS security still remains as an ongoing challenge in modern computer networks. So now let's take a look on the applications of DNS. First, web browsing and URL resolution. Like every time we type a website like youtube.com, the DNS immediately translates it into an IP address so that our browser can find the server. Without DNS, the internet would nearly be unusable for regular users. Email delivery or routing is another major use. When you send an email, the DNS helps locate the recipient's mail server so that the message reaches the right input box. It can also be used in cloud computing and CDNS. CDNS meaning content delivery networks. The cloud computing and CDNS also rely on DNS. The CDNS use DNS to direct users to the server that's the closest to them, reducing the latency and speeding up content delivery. The DNS is also key for load balancing and redundancy. Companies can distribute traffic across multiple servers using DNS techniques, ensuring that no single server gets overloaded. Other applications include virtual hosting, when multiple websites share one server but are identified by separate domain names, and internal security, where DNS firewalls can block malicious sites before a user even reaches them. Now let's take a look at the limitations of a DNS. Despite its advantages, the DNS does have some limitations that we should be aware of. First of all, security vulnerabilities are a very big concern. Without extensions like the DNSS EC, the DNS can be targeted by attacks such as cache poisoning, which can redirect the users to malicious websites and therefore loss of data. There's also an issue of an initial resolution delay. Like when a user types a domain name, the request has to travel through several DNS servers before resolving to the correct IP. This can add a small but noticeable delay. Another issue of the DNS is the dependence on the DNS infrastructure. If the DNS servers go down or become unreachable, access to websites can be completely blocked even if the servers hosting the websites are completely fine. Misconfigurations can cause service failures too. A single wrong entry in a DNS zone file can make an entire domain completely unreachable. Additionally, the DNS is also inherently a public system, which can expose queries to third parties, raising privacy concerns. Some advanced setups like the DNS over the HTTPS are helping, but it's still very much a limitation. Lastly, propagation delays can be quite frustrating. When the DNS records is updated, it can take hours for changes to reflect across the globe, meaning updates aren't instant. Finally, to conclude, DNS is a fundamental service that makes the internet user-friendly. It translates the domain names into IP addresses and enables efficient communication. Without DNS, modern internet usage would not be possible. Thus, DNS forms the backbone of internet communication in computer networks. Thank you.